Hi class, this is Coach Riza. In this video, we are going to talk about General Chemistry 2. But before we proceed to the main topics, let's have a review of some of the topics that we had from General Chemistry 1. So the topics from General Chemistry 2 is also related to General Chemistry 1. They are interconnected to each other. So let's have a review from our General Chemistry 1. So first, the question is, what is matter? What is matter? It is anything that occupies space and has mass. So, as we all know, there are states of matter, and we have 5: solid, liquid, gas, plasma, and Bose-Einstein condensate. For this topic, for General Chemistry 2, we are going to focus more on the first 3 states, which is the solid, liquid, and gas. First fact about matter is that matter is made up of small particles. As we all know, solid, liquid, and gases are composed of molecules, atoms, and even smaller particles like the protons, neutrons, and electrons. So that is why matter, as we all know, is made up of small particles. What can you observe from this illustration? From our solid, liquid, and gas. So as you can see, class, the particles have spaces between them. Okay, may it be solid or liquid or gas, they have spaces in between them. And these spaces are what we call the interparticle spaces or intermolecular spaces. Another fact about matter is that the particles of matter attract each other. So there are attractive forces between atoms or molecules, and this becomes stronger as the particles move closer together. These attractive forces are what we call the intermolecular forces. So we actually have 2 types of force. So we have the intermolecular forces and the intramolecular forces. So it's intermolecular and intramolecular. So what is the difference between the two? So when we say intermolecular forces, these are attractive forces that occurs between the molecules. It is between the molecules. That is why intermolecular forces. While the intramolecular forces are forces that holds atom together in a molecule, also known as bonds. So as you can see here in our illustration, the bonds that I'm talking about, the intramolecular forces, are this one. Okay, so these are the bonds. These occurs within the molecule. So it's the force that holds atoms together in a molecule. While the intermolecular forces, these are the attractive forces that occurs between the molecules. Okay? Intra, within, inter, between the molecules. We have here a drop of ink in water. What have you observed? As we can see, class, the drop of ink in the water spreads out. So it occupies the spaces in between our water. So aside from that, what really happens is that the particles of matter are moving. They are in constant motion. Particles of matter can move because they have energy. That's why they can move in constant motion. And as you can see here in our illustration, these are the particles of gases. And as we can see, they are moving at random motion. That is because gases has higher energy than the other states of matter. An example of this is when you're in a room and someone sprayed a perfume. So of course, the smell in the form of vapor or gas will travel within the room. That's how we can observe this, that the particles of matter are in constant motion. It's because, again, the particles of the perfume has energy. That is why it can move in random motion within the room. That is why we can smell the perfumes. So the first fact about matter is that matter is made up of small particles, and then the particles of spaces between them. And particles attract each other, which we call the intermolecular forces of attraction. And the particles of matter are in constant motion. They can move. They have energy. That's why they can move. And this four postulates is the definition of our kinetic molecular theory of matter. Okay, so kinetic molecular theory states that matter is made up of small particles and they have spaces in between them, which we call the intermolecular spaces. And the particles attract each other, which we call the intermolecular forces. And they can move in constant motion. So matter can move in constant motion. So that is the kinetic molecular theory. Moving on to the state of matter, solid, liquid, and gas, as I have said a while ago, we're going to focus more on this three. That is why we're going to review the characteristics and the properties of our solid, liquid, and gases. So first, we have solid. Solid has definite shape. It has constant volume. It's nearly incompressible. The particles are very close to each other, just like in this illustration, and the particles vibrate in fixed position relative to one another. Yes, they do move, and that's because they have energy, but they're still in solid form. Okay, the particles only vibrates on its place. So the intermolecular spaces of solids are very small. As we can see in this illustration, that there are small spaces in between. And because of that, the intermolecular forces that holds these molecules together is stronger. When it's in solid form, the intermolecular forces is stronger, so it holds the molecules together, making it solid. Next state is liquid. So liquid has no definite shape and it takes the shape of the container. So it has constant volume and slightly incompressible. The particles are neither too close nor too far from each other. And of course, this is the typical illustration of our liquid. So the particles of liquids also moves. They move freely among themselves, but they are still clumped together. So the kinetic molecular model of the liquid is like this. As we can see here in this illustration, they are moving. Just imagine that they are flowing. They are freely flowing. Just imagine that they are freely flowing. Okay? And the intermolecular spaces of liquids are a bit larger than the solids. Okay, not too far and not too close to each other. Just the right distance in between. And the intermolecular forces is less weaker than the solids because again, there's larger spaces in between than the solids. But this is still strong because again, the intermolecular forces hold these molecules together. That is why liquid, as we can see it, it's fluid. It can flow, they are still clumped together, and they are liquid. So it stays as it is, liquid as a liquid. It's because of the presence of the intermolecular forces between the molecules. So last but not the least is the gas. So gas has no definite shape. It takes the shape of the container. It has no definite volume. It can be expanded or compressed. Particles are far apart. Actually, they're very far apart from each other, and the particles are independent of one another. So particles move in random motion. As I have said a while ago, the gases has more energy than the first two states of matter. So that is why they can move in random motion, and they really move fast. Okay, as we can see here in our kinetic molecular model of gas, so it's like this. They move in random motion. They are very far apart. So the intermolecular forces is very weak because again the intermolecular spaces are very large. Okay, they're very far apart. That is why they have a very weak intermolecular forces. So that is the state of matter, and we have talked about this before in our general chemistry 1. With the addition of kinetic molecular theory, we found out that solids can vibrate on its own place, and liquid can move freely. Gases can move in random motion, as shown in our kinetic molecular model. So the next part that we are going to talk about is the chemical bonds. Chemical bonds are force of attraction that holds two atoms together in a molecule or ion pair. So bonds are formed either by transferring or sharing of electrons to achieve a stable configuration called the octet rule. Octet rule. Elements tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electronic configuration as a noble gas. So literally, every element tends to bond to each other to achieve the electronic configuration as same as the noble gases to become stable. So there are different types of chemical bonds. We have the ionic bond, covalent bond, and the metallic bond. But for this lesson, we're going to focus more on these two, covalent bond and ionic bond. Ionic bonds form between metal and nonmetals. When metals lose electrons, it becomes positively charged, while nonmetals becomes negatively charged, and when it accepts electrons. So ionic bonds involves in the attraction between two charged ions, and these bonds hold the ions together in an ionic compound. So in writing the formulas of ionic compound, we use the crisscross method. Okay, so the charge, if it's numerically equal, no need to crisscross since the sum will be 0. And the subscript 1 is not written. So let's see the example. So we have here two combining elements. We have a metal and a non-metal. Sodium, as we all know, is a metal. That is why it will transfer or it will give up its electron to chlorine. So giving them a charge. For sodium, we have positive 1, and chlorine, we have negative 1. Okay? So it's because, again, sodium lost 1 electron, and chlorine gained 1 electron. So that is why they have a positive charge for sodium and a negative charge for chlorine. So this is also the ions, the sodium ion and the chlorine ion. And the charge values here is the valence. Okay, positive 1 and negative 1. And the formula, if we use the crisscross method, this one will go here and this one will go here. But since they're both the same, when we get the sum of this, positive 1 plus negative 1, it will become 0 because of the sign. It will cancel out. And aside from that, we don't really write the subscript 1 in the formula. So that is why sodium chloride is this one. Next is the covalent bonds, also called as molecular bond. It's a chemical bond that involves the sharing of electron pairs between atoms. So again, it is sharing of electrons. So a while ago, ionic bonding is said to be transferring of electrons from a metal to a non-metal. But for covalent bond, it is the sharing of electrons, okay, between atoms. So these electron pairs are known as the shared pairs or bonding pairs. So covalent bonds are formed between two non-metal atoms. So take note, between two non-metals with identical or relatively close electronegativity values. So we have here a single covalent bond. Of course, it forms a single bond. Double covalent bond, it forms a double bond. And triple covalent bond forms a triple bond. So covalent bonds, the compound that consists of atoms bonded together by shared electron, is called molecular compound. So examples of molecular compounds are the diatomic gases, which is made up of atoms of the same elements, like this example. And we also have the binary acids, which is hydrogen, a nonmetal element that shares electrons with halogens to form binary acids and to achieve stability. As we can see, we have their HCl or hydrochloric acid, HF hydrofluoric acid, and so on. That is why they are called binary acids. So we have here a table wherein we can see the combining of our atoms, how they are how they bond together. So we have HF, hydrogen, and fluorine. Hydrogen has 1 electron, while fluorine has 7 electrons. So they both need 1 electrons for them to become stable. That is why they're going to share that, as we can see here. So they are sharing their electrons to each other. Okay, so we have here pH 3. This is phosphine. Okay, and we have here phosphorus. There is 5 electrons, while hydrogen, there are 3, but each has 1 electrons. So phosphorus need 3 electrons, while hydrogen for each need 1. So as we do the electron dot formula, we can see the sharing of electrons from our phosphorus and hydrogen. So that is our covalent bonds. Okay, so that's how we do the electron dot formula for our covalent bonds. Now let's move on to our main topic, which is the bond polarity. Electron sharing in covalent bonds may be equal or not between two atoms. So example is that when a diatomic molecule containing atoms of same element, electrons are shared equally. When a diatomic molecule containing atoms of different elements, such as HF, the shared electrons are pulled more towards the vicinity of fluorine. So these situations resulted into 2 kinds of covalent bonds. So meron palang 2 kinds ng covalent bond, namely polar and the nonpolar covalent bond. So let's find out how this happened. How can we identify if it's a polar or a nonpolar bond? First is a nonpolar covalent bond. So a nonpolar covalent bond, the electrons are equally shared between atoms. So this means their electronegativities are almost the same or exactly the same. And examples of molecules that have nonpolar covalent bonds are this one, the diatomic gases. As you can see, class, the elements bonded together are the same. Okay, so we have here 2 hydrogens, 2 fluorines, 2 chlorines, and so on. So if we look at the structure of our diatomic gases, so we have here hydrogen bonded to another hydrogen. They both have the same number of electrons. So they only have 1 electrons for each. That is why they are sharing their electrons to each other. So meaning to say they are equally sharing those electrons. Same goes with our fluorine bonded to another fluorine. They have the same number of electrons and they only need 1 for each. That is why they are sharing their electrons to each other. So they are equally sharing their electrons. So aside from that, we can also see the electronegativities of these elements. So for hydrogen, the electronegativity is 2.1. So since it's the same element, so they have the same electronegativity value. That is why if we get the difference between the two, 2.1 minus 2.1, it's equals to 0. And that means it's a nonpolar covalent bond. So the bond existing between the hydrogen to another hydrogen is a nonpolar covalent bond. Next is polar covalent bond. For polar covalent bond, electrons are shared unequally, not equal. Okay, so resulting in one atom being partially negative and the other being partially positive. So examples of these are like the binary acids. So we have here hydrogen bonded to fluorine. So how does this partial charges happens? So the partial charges happens because the electrons are shared unequally. They are not equally shared between these two elements. Why is it that it's not unequally shared or it's not equally shared? It's because of what we call the electronegativity. So before I explain this to you, this part, we're going to check out first what is electronegativity. So electronegativity of an element is the tendency of an atom to attract electrons to itself when it's chemically combined with another element. So basically, if you have a higher electronegativity value, the attraction is much stronger. The attraction of electrons towards itself is stronger. The four most electronegative elements are fluorine, oxygen, nitrogen, and chlorine. Going back to our polar covalent bond, so we have an example, hydrogen bonded to fluorine. So why is it that it has partial charges? It's because of the sharing of electrons is not equal. Why is it not equal? Because of the difference between the values of the electronegativity. For hydrogen, it's 2.1. For fluorine, it's 4. So they have different values. That is why the tendency of fluorine to attract electrons towards itself is more stronger than the hydrogen. Okay, so fluorine attracts electrons more strongly than the hydrogen. Okay, so they both have electronegativity value. They both can attract electrons. It just so happened that fluorine has a higher value than the hydrogen. That is why it can pull the electrons towards itself. So as you can see, the fluorine end here of the molecule has higher electron density, okay, than the hydrogen. It's because again the electrons are being pulled towards, or it's attracted towards the fluorine. So we can say that the hydrogen fluorine bond is a polar covalent bond. So the difference between nonpolar and polar covalent, just remember, for polar covalent bond, the electrons are shared unequally. Why is that? Because again of the presence of the electronegativity values. So these two are different because they're different elements and they have different electronegativity value, which results to the partial charges. For hydrogen, it has a partial positive because it kind of like it's losing an electron, while fluorine has a partial negative because it kind of like accepts the electron. But take note, class, this is a covalent bond. Covalent bonding happened to this too. So it means they are still sharing their electrons. It just so happened that the electrons are more attracted to fluorine because fluorine has higher electronegativity than hydrogen, creating the partial charges. So that is why it's a polar covalent bond. So for nonpolar covalent bond, just remember the electrons are equally shared between the atoms. So usually the electronegativities are almost the same because again the elements or the atoms bonded together are the same. Okay, so examples are the diatomic gases. So that is our bond polarity. Okay, so we're talking about the bonds. Okay, the difference between the nonpolar and the polar covalent bond. Now let's go back to electronegativity. As I have said a while ago, electronegativity is the tendency for an atom to attract electrons to itself. Okay, so again, the higher the electronegativity value, the higher or the stronger the attraction. So as we can see here, we have a periodic table that shows the electronegativity values of our elements. And as we can see the red arrows, it shows that the more we are going to the nonmetal area of, or the part of our periodic table, the nonmetal part, the more we can see the trend of our electronegativity values. It's higher in this area than the rest. Okay, so it's because again nonmetals usually has a higher electronegativity values than the other elements. Take note, class, hydrogen is also a nonmetal. That is why it has a high electronegativity value. Now let's move on to electronegativity difference. Now electronegativity difference is a factor that we can use to determine the type of bond in our molecule. So the electronegativity difference provides an estimate. So there's a range given, an estimated range to determine the type of chemical bond that most likely to exist in a compound. So there is a given range. So for ionic bond, It's formed when difference in the electronegativity is equal to or greater than 1.5. Nonpolar covalent bond formed when difference in electronegativity is 0. And the polar covalent bond formed when electronegativity difference is less than 1.5 but not equal to 0. So let's have an example. Let's say we have sodium and chlorine bonded together. Okay, so let's just say we don't know yet the type of bond. So we have here sodium bonded to chlorine. So the values are 0.9 for sodium and 3 for chlorine. So we only have to do is to just subtract regardless of the sign or sign. Okay, so 0.9 minus 3 is equals to what? It is 2.1. Okay, so it's 2.1. So that is the electronegativity difference between the sodium and chlorine. So for the type of bond, we can now identify what type of bond happened between sodium and chlorine. So from here, we can see the value or the difference, electronegativity difference that we got from sodium and chlorine is 2.1. So as you can see, it already falls here. Okay, so it's greater than 1.5, so it's ionic bond. Take note, class, ionic bond is a bond between a metal and a non-metal. So automatically, sodium chloride is or has an ionic bond between them. So let's have another example. Let's say we have hydrogen bonded to another hydrogen. So it is 2.1. So of course, if we get the difference between the two, it will be 0. So as we can see here, the value falls here, the nonpolar covalent bond. It's 0, the electronegativity difference. So that is why it's a nonpolar covalent bond. Now for the polar covalent bond, let's say we have an example. Hydrogen bonded to oxygen in a molecule which is water. Let's say it's a water molecule and we are trying to find what type of bond happened to hydrogen and oxygen. So hydrogen is 2.1, oxygen is 3.5. Okay, so it is equals to, the electronegativity difference is 1.4. So let's find out if it falls to a polar bond. So again, polar bond or polar covalent bond is formed when the electronegativity difference is less than 1.5 but not equal to 0. And it's correct, 1.4 siya. So it is a polar covalent bond. So as you can see, class, it's easier to identify the type of bond if we get the electronegativity difference. So there are different range, depends on the reference. So the one that we saw a while ago is from a senior high school book. This one is from a college book online. As you can see, it's more detailed than the other one. So you can see the electronegativity difference, the type of bond, if it's a nonpolar, polar, very polar, or slightly polar, and then ionic. So just take note, class, if it's ionic, it's between a metal and a non-metal. Okay, so the covalent bonds, it's between non-metals. So using the electronegativity difference, it will be easier to identify the type of bond. So there is another one. I got this again from a source from the internet. So it has a different range from this one, but basically they are the same. They are used to predict the bond types. Again, it's the estimates. As I have said, electronegativity difference provides estimates. So they are estimated values or the electronegativity difference. Now let's move on to dipole moments. So dipole moments occur when there is a separation of charge. So they can occur between two ions in an ionic bond or between atoms in a covalent bond. So dipole moments arise from differences in electronegativity. So in short, dipole moments usually can be observed on polar bonds or polar covalent bonds. Aside from ionic, it's usually observed in polar covalent bonds. So again, because there is a separation of charge and the difference in the electronegativity, there is what we call the dipole moments. So there is this presence of dipole moment, and the dipole moment is represented by an arrow. So this arrow is pointed always to the most electronegative element on the molecule. Okay, so more info about dipole moment. The larger the difference in electronegativity, the larger the dipole moment. So the distance between the charge separation is also a deciding factor into the size of the dipole moment. So dipole moment is a measure of the polarity of the molecule. So actually, class, dipole moment can be computed. So there is calculation for this one, but we're not going to like measure or calculate for this or the value of the dipole moment. Okay, so or the value for the polarity. But again, as we can see, dipole moment is a factor that we can use to measure the polarity if it's a polar or a nonpolar molecule. Okay, so dipole moment, again, the direction of the polar bond. So as I have said, they are usually observed in a polar bond in a molecule. So the arrow points toward the more negative electronegative atom, as we can see here in the illustration. So we have here examples. As we can see, bakit siya naging polar bond? It's because, again, the difference in the values of our electronegativities. So H is 2.1, chlorine is 3.0. That is why there is partial charges. And because there is the separation of charge, there is a dipole moment. Kaya may dipole moment here because, again, this is a polar bond. Another example we have here, water. Water, again, okay, it's a polar molecule. As we all know, water is a polar molecule. And if we look at the bonds between the hydrogen and the oxygen, it is polar bonds because, again, they have a different value for electronegativity, and because of that, there is partial charges and there is a dipole moment. And the structure of water is bent. Okay, it's bent. It's like this. Okay, so it's because, again, of the presence of the lone pairs, and it cannot be in a straight line because, again, there is the presence of lone pairs. They will repel this part or the bonding pairs, and that is why there is an angle to this one, the bent structure or shape, molecular shape. Okay, so that is the structure of our water. But as we can see, the dipole moment here is pointing towards our oxygen. So because they're on the same direction, this whole molecule here is a polar molecule. Take note, class, that not all molecules that have polar bonds are polar molecule. So we will see later on that even though the molecule has polar bonds, it can be a non-polar molecule. Okay, note the difference between the bonds and the molecules, class. So here we are, polar molecules. So a polar bond in a molecule can make the entire molecule polar, but not all molecules with polar bond can be polar molecule. So let's find out later on. So a molecule that has two pole or charged regions like HCl is called a dipolar molecule or a dipole. So don't be confused between dipole moment and dipole. So that's how it's called. It's dipolar molecule or dipole, the charge regions. So it's different from dipole moment. Again, dipole moment is present if there is a separation of charge, and that arrow, this arrow represents the dipole moment. As I said a while ago, the molecule can be polar or non-polar depending on the factors that we have to take note. So in determining the molecular polarity, we depend on the dipole moments and the molecular shape. For the dipole moment, we are more on the direction of the dipole moment. As I have said, even if the molecule has polar bonds, it doesn't mean that it's a polar molecule. We have to rely or we have to depend on these factors, the dipole moments and the molecular shape. So let's first analyze this nonpolar molecule. So we have now a nonpolar molecule. So it says here that dipole moments are symmetrical and it will cancel out. So when we say symmetrical, there is a symmetry. So when we say there is a symmetry, as we can see here, it's boron banded to 3 fluorines. We can see the symmetry. Boron is bonded to the same element, 3 fluorines. So that is the symmetry that I'm talking about. And because of that symmetry, the arrows are pointing to the opposing direction. Okay, these arrows is the dipole moment. How did this happen? So let's find out. So let's check first the bond, the type of bond present to this molecule. So we have boron and fluorine. As we can see, it has a dipole moment, meaning it is a polar bond. Boron is lower or has a lower electronegativity value than fluorine. Fluorine has the highest electronegativity value. That is why the dipole moment is pointing upwards, pointing towards the fluorine here. So here it's the same. It's pointing towards the fluorine because it is the most electronegative of between the two. Okay, so that is why, as we can see, the arrows are opposing direction. That is why the dipole moments will cancel out. These arrows will cancel out. Okay, as I have said, there is a computation for this. It's related to physics, but we're not going to talk about that. But just to give you an idea, if it's on the opposite direction, the dipole moments will cancel out. That is why even though these has polar bonds in this molecule, it's still a nonpolar molecule. As a whole, it's a nonpolar molecule. So now we have polar molecules. So the same with my example a while ago. So polar molecules is said to be that the dipole moments are asymmetrical, meaning there is no symmetry on the bonded or elements bonded to it. Why did I say that there is no symmetry? Take note, class, that oxygen still has lone pairs. We cannot see the electrons, but there is lone pairs here. Okay, so it is asymmetrical. Okay, so the arrows, the dipole moments, of course, has one direction. So as you can see, class, it's a polar bond because there is a dipole moment. And the dipole moment are pointing towards one direction. That is why this is a polar molecule. So as I have said, if it has an asymmetrical shape, there are lone pairs. Like what I have said a while ago, water, now the oxygen part has lone pairs. That is why it's asymmetrical. If it's asymmetrical, then it's a polar molecule. And aside from that, class, we have to check also the dipole moment. Again, the vital part or the important part is checking the direction of the dipole moment. So for this case, we have here CHCl3. There is no symmetry in here. Okay, so they are not equal. This is asymmetrical in shape. So we have here hydrogen bonded to carbon. Carbon has higher electronegativity value than hydrogen. That is why the dipole moment is pointing towards the carbon. Well, carbon has lower value than chlorine, so the arrows are pointing downwards. So all the arrows are pointing downwards. That is why it has a net dipole moment. So one direction only. So that is why it's a polar molecule. So what if we change this molecule into something else? Okay, let's check out the nonpolar molecule in the same shape or geometry. So we have here a nonpolar molecule. So this one is CCl4. So as we can see, right away we can see that it has a symmetry because the bonding elements are the same. So carbon banded to 4 chlorine atoms. So as you can see, chlorine has higher electronegativity value. That is why the arrows are pointing towards the chlorine. And as we can see also, although this is a polar bond, each bond is a polar bond, but the dipole moment is pointing opposing towards another direction. This polar bonds or this dipole moment will cancel out. So it is a nonpolar molecule. Some molecules have polar bonds but do not have dipole moment. So this occurs when the individual bond polarities are arranged in such a way that they cancel out each other. So like this, carbon dioxide molecule. So let's see how this will cancel out. So we have here a nonpolar carbon dioxide. It's in linear formation, the geometry of our compound here, or the molecule. Why is it that it's opposing direction? Carbon is at the center, oxygen is on the sides. So as we all know, oxygen, if we look at the periodic table, the electronegativity of oxygen is higher than carbon. So that is why here, the bond here is polar and the direction is here. The dipole moment is directed towards the left. And this one on the other side is directed to the right. So they are opposing direction. That's why the polarity will cancel out. The dipole moment will be canceled out. That is why it's a non-polar. So how will this become a polar? So if they have one direction, we can see that this compound can become polar. So we have our HCN bonded together, hydrogen bonded to carbon, single bond. This one, it's triple bond. Okay, just take note, this is a triple bond between carbon and nitrogen. So as we can see, we've already added the electronegativity values, and H is lower than carbon, so there is a dipole moment towards carbon. Carbon to nitrogen, so it's carbon lower than nitrogen, so arrow going towards nitrogen. And as we can see, they have one direction forming a dipole moment. So this one is a polar molecule. Okay, so as you can see, class, the difference, pag non-polar, opposite direction ang dipole moment. Pag polar, same yung direction or one direction yung kanilang dipole moment. So again, we have seen this before. BF3 is a non-polar because of the shape and the dipole moment, or the direction of the dipole moment. Tetrahedral, CH4, non-polar siya because again, carbon. And then bonded to H, 4H, there is symmetry. And of course, the dipole moment for this one, carbon, is electronegative than hydrogen. So this arrow will go to the carbon. So this one's going downward, this one's going upwards, this one's going to the right, this one's going to the left. So meaning to say this will cancel out. The dipole moments will cancel out. That is why it's a non-polar molecule. Okay, take note, class. The bond is polar. Take note. The bond between carbon and hydrogen is polar. But because of the direction of the dipole moment as a whole in this molecule or compound, it will cancel out. So as a whole molecule, it's a non-polar molecule. Okay? So again, we know this before. Now geometry is bent. H2O is polar. So another example, pyramidal, NH3. Polar din siya. As I have said, molecular shape and a dipole moment are very important in determining the polarity of our molecules. Okay? So, of course, it can be linear, bent, trigonal, planar, or tetrahedral. And for linear, it can be polar or non-polar depending on the direction of the dipole moment. So, we have bent, trigonal, planar, and tetrahedral. Okay, so that's it for our lesson for today. I hope you've learned something from this. The next or the following slides are just reference for you, which you can check it out later on.